from long weekend mood, right? So I will go slowly in the first few minutes just to go through some admins and motivate you all for the new problem that we are going to discuss today. It's about census problem, and we are going to learn data structure that can solve this efficiently than what you have known earlier from cs2010. Okay. I will start slowly. This is second lecture, and this will be the first main topic of cs2010. Some admins. I was informed last week that 2 of you have also took LSM 1302, and it also has a midterm test on Saturday, 22nd September, but in the early morning, 8 to 10. It nearly clashed with hours 10 to 12. For these 2 students, I have granted them permission to start later. But for the rest, you will stay at 10 to 12. I just want to know if there are any other issues with timing, because Saturday is no module is scheduled on Saturday. So if I schedule a task on Saturday, there is a probability it will collide, like casting. It will collide with some other lecturer's plan on Saturday. So is there any other person in this room who has issues with quiz 1 timing? Hopefully no. If no, then all the other students will have to take quiz 1 on 10 to 12. Same, nothing changed. Alright. Okay, tutorial and lab billing status. The result will only be out tonight according to SCORE's schedule. Right? There are 143 students today, so +1 from last week. I haven't figured out who is the last person. Last week when I set the quota, I set it to 140. So about 3 will not get it. Right? But don't worry, it's just there. The quota 140 is just there so that each lab group, each tutorial group have a similar number of students as possible. Right? If I increase the quota, then some group may have slightly larger, the rest will have slightly smaller. I will force everyone to go to different lab groups first, and then those who cannot get in, 3 or more, I will slot you. Not me. The person in charge will help you. Will give you the appropriate lab slot, right? But yeah, there will only be 140 slots for tonight. Okay. Please rank your preference carefully. All the data have been uploaded, have been put in the IVLE. So I have also made an announcement on that. If you go to IVLE, this page is very informative. Lots of data here, right? You just need to find the correct information. The information is here. Okay. Right, so these are the tutorial and lab slots that we have. If you still want to change your mind, you can still do it before end of today, I guess. Yeah. Next. Some announcements. Last week we have Code for Science contest. Now we also have one more contest. It's click fraud. I help in charge of this. So if you interested in, so for example, online advertising, you have usually if people like a certain advertisement, you click on it, right? When you browse the internet, but some people create a malicious program or hire someone just to click this advertisement, and that is not appropriate. So we want to build a tool to detect such action, right? So you're given a click data, and you have to figure out which one is real person, which one is not. If you think this is interesting, you can try registering here. Community DSG click fraud. I will send the slide later. Right. You will have a briefing next week, so if you want to know whether this competition is for you or not, you can come to this briefing next week. It has money prize, of course, 2,000, 1,500, and 1,000. Okay. This is what we are going to do today. we are going to discuss a problem. I give it a name, census problem, and this will be our background. I mean, our motivating factor to learn the first data structures in 2010, which is binary search tree. Right. At the end of today's lectures, I will give you a preview of the game system. One of your tutors, Yan Han, have spent his entire holiday doing this. He just finished it last night, midnight. So I'm going to show you the game system and give you a sneak preview of PS1, which will be open. Will be released next week. All right. Okay. So census. So many people, like governments, companies, and also me in this module, do census, or some people call it survey, for many purposes. Right. I want to show you SingStat.gov.sg. If you haven't looked at it before, then this is the website. So Department of Statistics Singapore collect a lot of data, literally a lot of data, and then they use it to decide policies. Right. For example, I want to show you this. Okay. If you heard National Day speech, you will heard something like this. That okay. The median age of Singapore population keep going up from years to years. This is from 2000, 2001, 2002, 2003, 4, 5. This is the population pyramid. Yeah, look at the bottom side. There are not that many babies. So my baby just contribute one here, female baby. Right, but see that there are lots of more young people from age 20 to 60 something. This is the workforce, right? Singapore workforce. But there are not that many children and babies. Imagine this going on for a few years ahead. If just keep like this, then there are not. This 10 years later, this group of people will be adults, right? And you don't have that many adults, something like that. So Singapore government uses this kind of statistics to decide policies. Then I want to highlight Sun Tzu, Art of War, Chapter 1. So who have read this book? Anyone have read this book? Or briefly go through this, one or two. There is a famous saying. I cannot speak Mandarin, so I'm not going to try reading this. Okay? So my pronunciation will be bad. The translation means, if you know your enemies, you also know yourself. You will not be imperiled in 100 battles. So if you know your strength, you know your enemy's strength. If you are better than them, you can fight the war, right? If you are worse than them, you have to decide things, whether to propose terms for peace negotiation, or you have to run away or something like that. Okay? If you know the strength of yourself, know the strength of your enemies, or in this case, my relative strength and my student's strength, then I can design this module in such a way that it's suitable for many, or if not most of you. Right? So that's why I do survey. Okay? So let's do some kind of survey here in 2010. I'm not going to give you a questionnaire and ask you to fill in things, because it's going to take a lot of time. So we're going to use technology. We're going to use technology for clickers. So I have distributed clickers to about 50 something of you. So if you bring your clickers, let's participate in the survey. Okay, I have to make a remark first that I already know this data. So it doesn't mean that I ask this to tell you to tell me what is the information. I already know the data. This data is for you. The result of this clicker. What happened with the clicker? Can anyone try clicking something? Cannot? Okay. I have to restart. Restart this. Wait for a while. Usually this kind of thing we have to close the program. Loading screen. Okay, I already know the data, so the result that you are going to see later on the screen will be for your information, because I already know it. And I want to give you the same information. Okay, can. Yeah, I have a reference to last year's data, and also I have a rough indication of your data. But the result that we are going to see later will be for your information. If you bring your clickers and you take it out and give me your codes. Alright. With this slide, while we are waiting, I want to highlight something that you will use in PS1. It's called range. And range is denoted by brackets like that, right? You have a square bracket, and sometimes you also have round brackets. There is a meaning. The square bracket means that this endpoint is included. It's called closed endpoint. The normal bracket like this means that this endpoint is not included. So look at the number 2, for example. 23 ... 24 means that if your age is exactly 23.0, this is today is your 23rd birthday, you select number 2. Or 24 close, 24 close bracket with the normal close bracket means that if today if tomorrow is your 24th birthday, then you still belong to category number 2, right? But if you are 24.0, it means that today is your 24th birthday, you should select number 1, something like that. Okay, that's the meaning of left open, left close, and right open. Right? So let's see the result. 5. Well, you're younger than last year. 5.2. Here, 2021. Last year's average is about 21 to 22. And yeah, okay, we still have 1% above 24. Last year we have one with 26, I guess. Yeah, one with 26. Okay, so this is the age profile. Majority of you are in 2021 and 1920. Second year undergrad. Okay, next. Your major. This module is compulsory for CS and CM. So I am expecting a high number there. And then we also have people from CEG. You study CG 1103 and then switch to this one and some other streams. What are your majors? Right? It should be a linear line from highest. It should be computer science, and then to the right must be lower and lower. Whether it's true or not, that's it. Okay. My data is the number 2 is higher actually, but the fact that it's slightly lower means that there are not that many CNM students taking the clickers. Okay, but the trend should be like that. I'm interested with the none of the above. Who clicked none of the above? Where are you from? From? Quantitative? Where are you from? Okay, so majority are from this, and we have very rare from other faculty. Next, this is interesting. This slide also always show me something about distribution of clickers, which is kind of always true every year, which is not that good. Well, let's see. Let me reveal the rule first, the results first before explaining. MOE says that local university must admit 70% locals, and it's true. It's true. If you look, if I have the SOC data, 70% of SOCians are Singaporean, including this module. But is that true with the clicker distribution? Let's see. It's not. Really, it happens several times. I don't know why, but I have to encourage locals to pick out the clickers and give me your quotes, because by the way, I have run out of the clickers. I run 2 modules, this one and IT1005 MATLAB. I have 120, 50 taken by this mod, 70 taken by the other mod. So I don't have any more clickers. But then, if you don't borrow the clickers, means that you don't have quotes, right, during during classes like this. So if you are struggling, you can't tell me during lectures. You have to tell me elsewhere. You have to tell me outside the lecture. Right? This is always kind of true every year, so I'm quite puzzled why. Right? I have to keep encouraging locals to pick up and try to be more focal. Okay, and yeah, that. Yeah, this one I roughly know, so I don't have to. Let's continue. This is another thing. Last week I gave you a distribution of my prediction of class distribution profile, something like that, right? So I want to know whether the one borrowing my clickers fits that distribution or not. And because I bet that majorities have B or B plus in 1020. Whether that is true. If that's true, means that your CAP should be around 3 to 4, or maybe 4 to 5, around these 3 numbers. Again, this information is for you, not for me, because I have the complete data. It's for you to know this group has what kind of distribution. Let's see. Okay, so 4 is majority, 3.75 to 4, right? And then number 9 is outlier. Number 9 I don't want to tell, right? And then this is a huge group, so number 8 is a huge group. So if you maybe we can still break this into pieces, but currently I group them together and see that this is the one that I said last week. In the last 1 week of course, we suddenly have lots of people from cross-fac taking this mod. Cross-fac student means that usually they don't have to, right? They don't have to take this mod, but they take. There is some reason behind that. This is one of the reasons. And this is my prediction, and it should be like that. Okay. Not my prediction. This is my data. My data says the average of CAP is about 3.6. That's the average CAP of this class. And your 1020. Okay, you have done 1231 or MA 1100 last week. Or what is 1020? After we go through this 10-minute exercise, I will briefly tell you more details on why we do all this. This looks more normal distribution, right? Looks more. And again, the average CAP, the average score is around here. Finally, this is something that I don't have. Something that I don't have. What is your among those who have clickers? What kind of grades that you want in this mod? And there is a huge difference between this mod and the other mod that I have last week. MATLAB. It's a first year course. First year tends to be idealistic. Means that they want A+. They gave lots of A+ codes. Second years suddenly becomes more realistic. So let's see whether this is true or not. not really true. Okay, right. So a true shape should be like this, right? But no, this is what I can give you. This shape, like this one, this shape. So there are more people willing to who wants a higher score, but then I can only accommodate a limited number. So there will be some. The quota is limited. If you want good grades, you have to fight for it. All right. Next. So what happened after we do all this? So after we do all this, then back after these lectures, I will look at it again and compare with my own data and see whether I have to adjust things or not. None of these are surprising because it's matched with what I have. I have the full data, so it's roughly matched. The only difference is probably this slide, because this slide is the one taking my clickers are from the high side of the curve based on 1020 records. So I have to make a remark that for all pop quizzes appearing in my lectures, if you see a lot of correct answers by your peers who have clickers, don't be alarmed. These are the ones who did A or A plus in 1020 previously. Most of them, based on this profile. I will check my data again. But because there are lots of locals here who don't have my clicker, so they cannot give me my vote. You cannot give me your vote. Then if during pop quizzes you feel that, hey, I got it wrong. These 50 of them got it correct. I got it wrong again. Another 50 got it correct. If this keeps happening, remember that I have these sessions. You can look at it and see that in certain weeks, and maybe this Saturday if need be, there will be sessions for those who want to catch up. Right? So if you are in that position, because the result of breakers will tell you some information, don't hesitate to contact me. Right? So let's move on to the main part of the today's material. So after you get this data, you will do number crunching. We only have 50 people with clickers, so the number is not that big. But imagine if you are a Singapore government working with Singapore statistics information. You are dealing with 5 million some entries. Are you going to use a lot not so good data structure to store those information? No. You will need an efficient data structure so that questions about data can be answered quickly. So I will give you a subset of the questions, a subset of potential questions that you probably have after you have a census data. Okay. Let's restrict ourselves, concentrate on one aspect, age. The first slide that I posed earlier. What is your age? Right? And to simplify these lectures, I'm going to assume that students' age range from 0 to 100. That cannot be negative. For simplicity, it's all integers. And again, for simplicity, all distinct. And the numbers shown in the next few slides will be some random values that doesn't really reflect this class distribution of age. And because sometimes I have very small age and have near 100 age and so on. Okay. Then I'm going to ask several questions on this data. I want to know whether there are students with a certain age. I want to add new information. I want to add one more student with certain age. I want to determine who is the youngest and who is the oldest in this class, for example, or in this data. Okay. I want to list down all the ages in sorted order. Sorted can mean two things, can be ascending from small to large or descending from large to small. And I also need to answer 3 more queries. I want to find a student slightly older than certain age. For example, I'm 30. I want to know, is there anyone greater than 30 here in this class? The answer is no, right? Anyone greater than 30? Just now I have one greater than 24. No. And then the sixth task is to delete. So after number 2 is insert, you have 6 delete. This student, for example, left the class or left the module, so I have to remove this information. Then the last question that I want to do is determine the median age of the student. Right. So last semester you learned in cs2010 you learn about array or researchable array of factors, and we have for array we can have 2 things. One is a sorted array, or the other is unsorted array. So if we stop at this knowledge, if you graduated from associate without taking cs2010, you will probably end up, if you work in software company, you have to support the 7 operations. You may end up using this array and then having a very slow performance. Okay, let's see. So if we have an unsorted array, for example, we have an array of 5, 7, 71, 50, 23, 4, 6, 15. These are not sorted, right? Not sorted. And these values are random, right? It's not reflective of this class age, the age of student in this class. Okay, suppose I want to search whether there is a, do I have a student with 50 years old? Then say yes, I have 50 here, right? I have 50. Do I have 51? No, I don't have. So what is the worst case? The worst case happens when the number that I'm looking for is not in this array. Then I have to go through everything and decide, I don't have that. So it's ON, where n is the number of, see that we have an unsorted array of size n. N is 1, 2, 3, 4, 5, 6, 7, 8. 8 here. N equals to 8. So if I have 8 items in my array, to search for whether there is a student with a certain age, I need to go through 8 times. And if I have n items, n students, I have to go through n times, or n. What if I have to insert a new student? Because this is unsorted, quite easy. I put the new student at the very back. By doing so, I just extend my array by 1 more, and I don't have any gaps in between. So this process is fast. O1 is very good. Constant, 1 step. Constant means several constant steps. Just put this student at the very back. What if we want to determine the youngest and oldest? This is last week's lecture, right, on finding the mean and the max. You can scan through everything once and determine, keep the running mean and the running max. At the end of one pass, you know who is the minimum, who is the largest. What's the minimum and what's the largest? It's ON again. Okay? And then if you want to list down the ages of students in sorted order, in 1020 you have learned various sorting algorithms. Something like this. Something like this. So, for example, you learn about bubble sort, selection sort, merge sort, and so on. Maybe you do something like this. Merge sort, something like this. You keep chopping the list into 2. Sort the first half, and then recursively sort the second half. The second half done. Okay, second half done. Merge everything. You have the complete list. It's merge sort. It is n log n. So if you use merge sort or some other efficient sorting algorithm, you can sort these numbers in n log n, and then show these numbers after it's sorted. How about finding a student slightly older than a certain age? There are 2 ways. First, you sort it first, find the position of this age, and report the one next to it. But then it requires n log n, right? You need sorting first. There is a slightly better way. We don't need to sort. We just scan through everything again and keep track what is the smallest age that is slightly larger than the certain age. For example, I want to look for what is the largest number after 6. The answer should be 7, right? So you say 5, oh no, it's smaller than 6. No, 7, it's larger than 6, but so you keep the 7. 71, also larger than 6, but it's larger than 7, so you ignore. And so on. After you scan through everything, you will know what is the age that is slightly larger than a certain age. It's smallest among all other possible options. Okay, so again, one pass. You have to scan through one array and determine the answer. Now, how about deletion? Insertion is easy, right? Put at the back. But how about deletion? You first have to search for the one that you want to delete. It's ON already. Then once you find it, if you just remove it that way, you will leave a gap, a blank in your array. You leave a blank. So if you leave a blank, there is a problem with searching later. Suppose I have A, B, C, D like this. I delete C. If I delete C and I stop it like that, then future search will have problems. If you want to search whether D exists or not exists, this one, blank. Then should you stop here or should you continue? You cannot stop, right? Because this blank doesn't mean that this is the end of our array. There can potentially be other numbers at the back. So, no choice, you have to scan until the very last. Then the complexity of your search is no longer ON, where N is number of items, but O, the size of array, until you run out of the array. Okay? So, if you don't, when you delete, you don't do what we call closing the gap, then we will cause other operations to have problems. So when we delete C, we shift everything on the right of C to the left. So we have A, B, D, closing the gap. By doing that, we don't have our search performance will remain at ON. Okay. By doing so, if I delete the very first item, I have to shift everything to the left. ON. Right? How about determining median? Right? To determine median, the middle element, I have to sort it first. There is one option. I have to sort it first. And once I have a sorted list, the middle one is the answer. But then later in tutorial 1 and also last week, I already give you a hint. You can actually do this in ON. Right? If you know the correct algorithm. Tutorial 1. Next week, you will see this in detail. So, see that if you only use unsorted array, we have lots of out of these 7 operations, many of them are ON or N log N, right? And this is not small. ON and N log N is not small in terms of data structure operations. But you may have told me that, hey, wait, in 1020 we also learn about sorted array. And usually after sorting, things become slightly easier. Is that true for this problem? Let's see. So if we sort this array first, the same numbers, if I sort them first, I have 4, 5, 6, 7, blah, 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 until 71. It is sorted. So if I want to do the same 7 operations on this sorted array, things will get simpler. For example, searching. If I want to search whether a number is exists or not exists in this sorted array, I can use what you have learned last time, binary search. Start with the middle one, decide whether I have to go left or right, or whether the middle one is the answer. This is a logarithmic 2, because you keep dividing the search space by half. Right? Last week I gave you a trick question with linked list. Linked list in a sorted linked list you cannot binary search because there is no notion of index in linked list. If you want to search go for nth item, you have to start from the head, move forward n times, n minus 1 times. Here in array you can do that. You can use index to jump around. Right? So in a sorted array we can use binary search in log n. How about if we insert a new student? This time we have a slight difference. If last time in an unsorted array, if you want to insert a new student, you just put it at the back because sorted, not sorted, you don't care. But here you want to keep maintaining this array to be sorted, because if not, then once you add a new data, the array from sorted becomes slightly unsorted, then your future binary search will be wrong. So you have to keep your array always sorted at every time, at each time. So when you insert, you have to do a kind of insertion sort. To put the new number in the correct place. For example, I have a number 70. I cannot put 70 at the back of 71 because then I have 50, 71, 70 wrong. I have to insert 70 in between of 50 and 71. So I have 50, 70, 71. So it's kind of insertion sort. Last week, I gave you a pop quiz on which is the best sorting algorithm. You already have a sorted array. I put one wrong, right? One wrong. How to put this in the correct position. The best way is to use insertion sort. This is ON. And with one pass, you can slot the new number in the correct position. How about determining the youngest and oldest? Now this becomes easier. You don't have to do anything. The smallest will be in the front, the largest will be at the back. If you sort the array in ascending order. So it's O1. See that the numbers change, right? The fact that your array is unsorted versus the fact that your array is sorted, the complexity of certain operations are different. You can use different algorithms. Next, list down the ages of the students in sorted order. It's already sorted. So what you need to do is to enumerate one by one from left to right, right? One pass, ON. Find a student slightly older than a certain age. Okay, there are several ways, but the best way is to binary search that number and report the one next to it. But you want the one older than a certain age. What if the one that you are not you're looking for, if the certain age given here is not in the list, not in the sorted array? For example, find a student slightly older than a certain age 24. Then the answer should be 50, right? But 24 is not in the list. Fine, you just binary search the position of 24. You will end up in 23. But this is not what you're looking for, right? But binary search can still report this, and then you report one next to it. So whether the number exists or not exists in the sorted array, finding another number slightly larger than the target value is still doable with binary search. Now how about deletion? Same thing, same situation with that. First you have to search for it, log n. You can find what you want to delete in log n because it's sorted. But then if you just leave it there, you just leave it blank, you will complicate future binary search. Suppose you binary search and your sorted array have lots of blanks. If the middle element is blank, now should you go to the left or should you go to the right? You don't know. If you have a sorted array and the middle element is blank because you deleted it before, now your binary search should go to the left or to the right or report that the answer is there. Cannot. Right? So there's no choice. Even though you can binary search the location of the item that you want to delete, you still need to close the gap. So this is the issue of using array. You have to close the gap. Again, closing the gap is ON. How about determining the median? Because the input is already sorted, the median is right in the middle. O1, right in the middle. Okay, so this is a summary. Look at that. These 7 operations have 2 choices from what you have learned in 1020. One is unsorted array, one is sorted. The red ones are the weaker among the two. Right, so for example, searching is in unsorted array, you can only search everything, ON. In sorted array, you can afford to use binary search, log n. So log n is better, ON is worse. So I highlight the worst one. Okay, notice that even on the sorted array, you have problems with insertion and deletion. It runs in ON. Why ON is a problem? Why ON is a problem? How many of you use Apple devices? Or if you use Windows, it's hourglass, right? A moving hourglass. So imagine that n is 1 million. Every time you want to insert a new student, you go through 1 million times. If 1 million is too small for you, what if n is 1 billion? Every time you want to add one more, you go through 1 billion times. It's very slow. You will see this hourglass. So if you build, for example, for C&M student, you build a video game, and you use array for everything, even sorted array for everything. Then you may end up doing this with your gamers. where you want to load a new level, you wait for 10 seconds or wait for 1 minute. Are people going to play your game? Sooner or later they will leave because your game is too slow. Okay. In the next part of this lecture, I will highlight a binary search tree. These are the data structures that we want to learn in cs2010. Hopefully, the previous few slides have motivated you enough that ON is not good for large N. If you have a data structures where where some of the operations run in ON, and the N that you are going to play with is a large number, it's not going to be good. I will say that later in binary search tree, you can do things in log N, logarithmic N. This picture will gives us a perspective. What's the difference between N and log N? So when you have N equals to 8, log 2 of N is just 3. 2 power of 3 is 8. You have 16, log N is 4. 32, log N is 5. See that when N grows two times larger, log N only add by +1. How about 1 million? Log 2 of 1 million is just 20 something. Actually 19 something, because it should be 1024 squared. Yeah. So 1 million, and 1 million, you just need, if you have a data structure that perform in all logarithmic N, you just need about 20 operations to complete the thing instead of 1 million operations. How about 1 billion with 9 zeros there? If you have an ON data structure, you will go through 1 billion times. But if you have a log N data structure, you just need 3 zeros. 2 to the power 30 is 1 billion. 1 billion, roughly 1 billion. You only need 3 zeros. 30 compared to 1 billion. How huge is that? I want to say that between log and N, the gap is very, very huge. Okay, so this is what we can do later after this lecture and next lectures. You will be able to run things in log N. So I'm going to give you an overview of binary search tree, and then in 10 minutes we'll take a break. So this is an overview of binary search tree, what is it about, and later in the second half we will go through the details of the operations that we can do in binary search tree. So binary search, you have heard this term before, binary search. Now I just append another term, tree, binary search tree. We abbreviate it as BST. The versatile and non-linear data structure. Why non-linear? I said linear data structure is if you can see the items in your data structure from left to right, right to left, top to down, bottom to up. You can view it that way, it's linear. But now with a tree, it's no longer like that. Right? So binary search tree. It's a tree. So if it's a tree from your 1231 knowledge, you have taken that module. Tree contains of nodes and edges. So every node or every vertex, nodes or vertex are the same. Of this tree, we have 4 information. That information are who is my left, who is my right, who is my parent, and what is the value that I want to store in this vertex. Left, right, parent, key or value or data. 4. And then every vertices in my tree, every BST vertex, observe this property. If this is your node, and you have a value or the key, certain value here, and everything on your left subtree will be smaller than the value of this key, and everything on the right of this value, this x, will be larger than x dot key. And for simplicity, I will drop the equal sign because the data that I'm going to use are all distinct integers. So you won't have equality problem there. So do you realize that this is binary search? This principle is binary search. If you already have a sorted array, if you guess the middle element, and what you are looking for is larger than the middle element, you know you have to go right. If it's smaller, you know you have to go left. These data structures uses that idea. So I will organize my data so that if I have a smaller item than the current item, I will specifically put it on the left subtree. If I have a numbers or integers greater than the current item, I will put it on the right. I keep doing that for everything. So I will have this kind of example, right? This is a binary search tree. Why? Look at the values. Starting from the root. The values of the root is 15 on 5. Notice that everything on the left of 15 smaller than it. 6, 4, 7, 5, all of them are smaller than 15. Right? And then everything on the right of 15 is greater. 23, 71, 15, in whatever order, is greater than 15. And realize that this is also a recursive definition. Right? So for 15 it's true. Everything on the left of 15 is smaller. Everything on the right of 15 is smaller. Now look at this subtree rooted at 6. So 6 is the new root of the subtree here. Right? 6. Everything on the left of 6, which is 4 and 5, are smaller than 6. Everything on the right of 6, which is 7, greater than 6. How about 23? Everything on the left, which is nothing, is smaller than 23. Everything on the right of 23, which is 71 and 50, are greater than 23. Can still do one more thing, recursively. 6 has 2 subtrees, 4, 5, like this. Everything on the left, which is nothing, smaller than 4. Everything on the right, 4 is greater than 5, greater than 4. 7 is already a leaf. By definition, a leaf is already a binary search tree for text. The left and the right is blank, so it doesn't matter. Okay, so we call those the first node that starts the tree is root, and then nodes without any other children is called the leaves. Anything else in between, everything else are called internal vertices, right? Including the root. Root is also internal vertices, but it's a special internal vertex. So, if we already organize our numbers like this, if we have a number, everything smaller than this number will be on the left. If we have a number, everything larger than this number will be on the right. Then we can use binary search. It is not totally new. We have seen binary search last semester. So let's do a kind of binary search using on this structure of numbers. Suppose I want to look for 71. My reference point is the root. So you can imagine that the root is your middle element in sorted array. So I compare 71 and 51. 71 and 15. 71 is greater than 15. Because I have organized my data in such a way that everything greater than 15 must be on the right of 15. Should I search the left side? No, don't have. Because I know that everything on the left of 15 here will be smaller than 15. So there's no point searching that way. I know if 71 exists, it must be on the right. So I go to the right subtree of 15. So I am now in the subtree rooted at 23. At 23, I repeat the process again. 23 and 71, who is smaller? Who is larger? 71 is larger. So I know I still need to go right. At 71, I compare 71 with 71. It's equal. So I know that, I found it here. So, another example, searching for 7, my favorite number. 15 greater than 7, right? So I know if 7 exists, it must be on the left side and not on the right side of 15. So I go to the left side. At 6, I ask again, 6 and 7, who is larger, who is smaller? Oh, 6 is smaller than 7. So I know that 7 must be on the right of 6. So I go right. I go here. I compare 7 with 7. Oh, I got it. Yes, I got it. So I say, yeah, I found number 7. Now, an example of finding non-existent entry. 22. Again, I can only start from the root. That's the first reference point that I have. 15, 22, I have to go right. 23 and 22, I have to go left because 23 is larger than 22. But when I go left, there's nothing here, right? Nothing. So I can stop here and say that because I have organized my data this way, I know that 22 is not in the tree. It's not in the binary search tree. So, can you see that now we can write this in a more formal manner as a function, the recursive function. Last week in my intro lectures, I already asked about recursion, and I found out that it's the same situation as last year. Majority still have difficulties with recursion, even among those with trackers. So there will be lots of more recursions in this module, and if you have difficulties, don't hesitate to contact me or TA. So how can we write this search procedure as a recursive function? So you are searching for the value phi in a subtree rooted at C. If C is null, means that it's an empty tree, you know that you cannot find it. So this situation. If C is a blank tree, you are looking for 22, but the subtree that you are looking for is now blank. You know that you cannot find it, so you return null. But if C dot key, if C is not null, means that it's something, it's a vertex, it's a valid vertex. If it's key equals to what you are looking for, you stop, you return this node. If C dot E less than V, you search on the right. The middle, the key of this vertex is smaller than what you are looking for. Means that the one that you are looking for, if exists, must be on the right side of your, must be on the right subtree of this subtree. So you go right, else you go left. This is very similar to binary search. So you link this with what you have learned last time. This is similar with binary search. One more try. Okay. This one will give us the complexity of search. Start from 15, compare with 51, you have to go right. Compare with 22, go right. Compare with 71, go left. Compare with 50, go right. But 50 is not there. So searching for 51 is one example where you have to ask many times. In fact, you have to ask the questions where the key and value, compare key and value from the root until the deepest leaf. Here, this is the root, and 50 is one of the deepest leaf. The other one is 5, right? Because 15, 6, 4, 5 is also quite deep. It's four steps, 3 steps. So what is the time complexity? So the time complexity, I'll just give you a quick analysis. The worst case is the height of the tree. Link this again with searching in an array, in an unsorted array, for example. You have to search from front to back. That's the worst case. Right? But here, after you organize the data like this, left, right, left, right, left, right, like that, the worst case is the one that you're looking for is not there, and the path that you have to take is from the root to the deepest possible leaf, or the height of the tree, OH. Okay? So we stop here first. We take a 5 to 10 minutes break until 10:04 maybe, 11:04. Digest this information. You have seen census problem, lots of theories can be performed on it. You only use array, it can be slow. Right? So in the second half, we'll continue with DST operation. Then you will have lots of duplicate. What if I have a big array, say 1 million? I keep inserting, deleting, inserting, deleting, then you will have lots of things. What if you delete C, then you take you copy D to that, then you have double D. Check whether you check the left and the right.
Yeah, if you encounter that empty cell, then you just take the left side.
Now, what if B and D also blank? What if everything is blank? You will complicate your data structure. Because you will complicate your own data structure. Your code becomes very complicated, and you can end up setting everything to the left and right. Become ON. It's a good idea. Okay. The answer is here, but you don't know which page. You can read everything. You master everything. I will not have to read it. November, for example. I have titles and everything. I have titles. Yeah. You can solve all these problems. This is about CFC. This is about CSC again. This is about C. You can solve everything. You probably don't need to. Yeah, maybe. For now, it's just like this. I don't want to have so many different. Yeah, I know. It's to minimize my cost. Okay, we will resume slowly while we're waiting for the rest to come back. A quick recap of where we are 5 minutes ago. I've introduced you a binary search tree property. where if you have a node, everything on your left smaller than it, everything on your right is larger than it. Doing this, you can apply a kind of binary search strategy if you want to search for your number or in your data. You start from the root, you decide whether that is your answer, or whether to go left or whether to go right. And you can do that here at worst in OH time, because the worst case is the item that you are looking for is not in the BST. You have to start from the root, go down to the deepest possible leaf. Deepest possible leaf means the entire tree, the height of the tree. So we continue with the next few operations on this BST. So of course, a data structure, you need to be able to insert and delete things, right? So we start from the simpler one first, insert. Okay, suppose we have an empty BST. If you want to insert 15, you just put it there, put it as the root, right? But then when you insert a new number 23 after you have 15, then you have to look at the root, which is 15. You have 23. According to BST property, if you want to put 23, which is larger than 15, you have to put it on the right of 15, right? So you put 23 on the right of 15. Otherwise, it will be wrong. Then if you have another number 6, you start from the root 15, you have 6. 6 smaller than 15, right? So you have no choice but to put 6 on the left of 15. You have 6 as the left subtree of 15. And so on. Okay? So quite simple, right? Insertion is quite simple. So now I ask you another question. Just now I insert 15, 23, and 6. But now what if I insert 15, 6, and 23 in that order? I swap the last two. I swap 6 and 23. Are we going to get the same BST or not? Okay, I have a picture. Inserting 15, 23, and 6 give us this. But if I insert 15, 6, and 23, I swap 6 and 23, will I get the same or different tree? The idea is, root, you just put it there. And next few numbers, you decide whether you have to put it left or the right on top of the existing ones. The same. Why? You put 15 as the root, you put 6 on the left of 15, you put 23 on the right of 15, you will get the same tree. You get the same. Now, what if I insert 6, 15, 23 in that order? So I insert 6 first, and after that I insert 1, 5. After that I insert 23, 2, 3. Will I get the same or different minus 3? Yep, you got it. It's different. You put 6 first. If you put 6 first, this 6 will definitely be the root. The root is no longer 15, and definitely you will have a different tree. Okay, so let's continue from this point. Now I insert 71. 71 must be inserted where? I compare with the root. It must be greater than the root, so I have to put it on the right. Then I have 23. I have compared 71 with 23. Again, it's larger, so I have to put 71 on the right. So I have to put 71 here on the right of 23. Okay, I put it there. Oh, but now I want to insert 50. Again, I repeat the process, right? At this point, 50 is smaller than 71, so I have to put it on the left of 71. So I have to put it here. Now, do you realize that now insertion will also run in OH? But insertion we always create a new leaf. Is that true? Every insertion to a binary search tree will always create a new leaf. And a new leaf means a deeper and deeper, possibly deeper and deeper tree. Possibly, not always. Suppose you already have a deeper leaf and you want to insert another number extending the height of the tree one level further, and insertion can run in OH. H is the height of the tree. Okay, it's a 4, 7, 5 in that order, then we will have the same here. And so how to translate this into a code? We can do insertion with two parameters, where we are now, in which product, and what is the value that you want to insert. We change the code a bit compared to searching. If now t is null, previously during searching you say cannot find it, return null. But here when it's null, you are happy. For during insertion, when you find a null, you're happy because that is your insertion point, right? So for example, here, when you find null 71, go to the left. Go to the left. This left is null, empty 3. You are happy because you are going to put 50 there. This is this is the place that you're looking for. This one. You want to insert 71. You go 15, 23, go to right, null, right? If there's a null here, you're happy because you can put 71 there. So the code is like that. Okay, the code is, if you find an empty sub-tree, this is your insertion point. You create a new vertex there. If it's smaller, you insert to the right. If the key is smaller than the target value, the value to be inserted, you recursively insert to your right sub-tree and update 2 pointers. Your right pointer, t.right, will point to this sub-tree, and t.right.parent will point to me. This is to link the pointers correctly, like in linked list actually. More details later. If the other way around, if it's smaller, you recursively insert it to your left. Okay? Finally, return tree. Return t. So these two lines, t.right equals to this new subtree, and t.right.parent equals to myself, is to fix the pointers. So let me highlight with this example. Okay, 71. I want to put 71 on the left, right? If I just create a new 50 without this age, so 50 will be created here, but 71 doesn't know where is 50. So I have to say 71.left is 50. But then 50 must also know that its parent is 71. So how? 71.left.parent is 71. Right? 71.left is 50, right? Dot parent is the arrow going back up is 71. So that's why you have this thing. T.left is insert on the left, and then t.left the parent is me. So I fix the arrows from me to the new child, and from the new child back to me. So the connection is there. Next. That's for insertion. Now the next task is task number 3 is to in the motivating example just now is to find the smallest and the oldest student, the youngest and the oldest student. It's equivalent to finding the minimum and the maximum item. If you have organized your data as a binary search tree like this, then do you realize that your minimum is always on the leftmost side, and your maximum is on the rightmost side? To be precise, the minimum is the one that doesn't have any more left children. The minimum element here is 4. It's the one that doesn't have any more left children. Why? Because based on BST property, if you are a certain number, you have a left subtree. Means that there is something smaller than you, right, in the tree. But if you are a certain number and nothing on your left subtree, means that you are the smallest possible. So the idea is to start from the root and always go left until you cannot go further left. That node is the answer. So you can write like this. If the current tree is null, it means you cannot find it. It's an empty here. You written -1. Nothing is minimum. Or you can use another symbol if you like. Yeah, if not necessarily has to be -1. If you are a certain value and your left is null, you are happy. This is your target. Because if you are a certain value and your left is null, means that you are the smallest possible. You return t.t as the answer. It's 4. Other than that, you recursively go to your left side. Keep searching to your left side. How about find max? This is the analysis is OH also, because you start from the root, and it can happen that the leftmost side is very, very deep on your left, you have to go through the entire height of the tree to find your leftmost point. Okay? For max, it's the reverse. You just change the wording a bit. You go to the right all the way until you cannot find anything else on your right. Okay. So far I have shown you searching, insertion, find min, and find max. I didn't say the complexity is O n or O log n or O something, but I say it's O h. H is the height of the tree. How high can h be? Right? So we organize the data in such a way that everything on smaller than me put on the left, larger on the right. It's like a binary search, right? So how tall the tree can be if I keep doing that. If I keep doing that. Let's see. Okay. Correct answer is number 3, ON. And 11 of you apparently didn't see the next slide. Yes. I can have a worst case. I can have a tree like that behaves like a linked list. This is a linked list. Although the name is a tree, you have 4 as the root, and you have left and right. But here in this case, you don't have left, or you always have right subtree. You can say that 4 is the head of your linked list, and 71 is the tail of your linked list. 4 go to 5, 5 go to 6, and so on. Linked list, searching in the linked list is ON, right? The depth of this tree from the root to 71, 4 to the deepest leaf 71 is the number of items in the tree. So the height can be as tall as n. Right? So can you spot one more worst case scenario using the same set of numbers? Okay, some of you make that gesture. So, do it in the other way. You start from 71 as your root and put 50 on the left, 23 on the left, 15 on the left, and so on until 4 is the leftmost node. Doing so, you will have another linked list, right? But the other linked list looks like that, from top right to bottom left. Yes, correct. So what's the point of using BSD? You say by using BSD I can get log n, but here you say that the worst case can go to ON. It's because my lecture is not complete. I still have the next lecture. Right? I still have the next lecture. Next week, I will share with you a way to make binary search tree really perform in log n. Here we have no guarantee, right? The height, the maximum height can be ON. But next week, we are going to see how to make the binary search tree always have a log n height, so that our performance can be better. But that's next week. Let's continue with the 4th task that I mentioned in the motivation slide just now. I want to list down all the practices in my data here, 4, 5, and so on, 4, 5, 6, 7, in sorted order. There is one tree traversal called in-order traversal that can also be written recursively that will be able to answer this efficiently. Right? So I start, code is like this. If I'm an empty tree, stop. Otherwise, I go left, I print what I have now, and I go right. So, from 15, it's not empty, right? So I go left. 6, not empty, right? So I go left. 4 is not empty, right? I go left. Empty 3 is empty, right? So I go back. I'm in 4 now. I visit 4, so I print 4. And I recursively go right. I'm now in 5. 5, I'm not empty, right? So I go left. Left is empty, I go back to 5. Print 5. And then I go right, empty. Go back. Go back to 6, print. Go right to 7, print. Go 15, 23, 50, and 71 like that. At the moment, my visualization tool doesn't have BSC animation yet, so no choice, it has to be PowerPoint like this. When it's ready, I will give you the link. My FYP student Albert is currently doing that. So using binary search, if you have already created a binary search tree, if you run in order traversal, that will visit left subtree first. When all in your left subtree have been visited, you visit yourself, and recursively go to your right. If you do that, you will get a sorted list. Just now I have shown you the first few. You can continue that process, and you should be able to get sorted list for everything. Yeah, you should be able to get a sorted list of everything. Okay. This I haven't explained, but let me just ask you this and give me your best guess. Give me your best guess. That kind of algorithm, in order left, visit, in order right, that kind of recursive algorithm, how slow can it be? I mean, what is the time complexity? I haven't teach you this. I will teach you this in the next slide. I just want to know, based on your guess, your feeling, your experience with data structure so far, or what will be your answer? You have a tree. The tree has n items. Right? You keep doing recursive right, left, visit, recursive right. What is the time complexity? If you don't know, guess. I will explain in the next slide. Okay, the CS code. Go ahead. So the analysis is not in your slide yet, but I have a quick way of doing analysis of in-order traversal. It's something that you probably haven't seen in 1020. It's called, you ask this question: how many times a vertex is touched during in-order traversal? How many times it is touched? The answers will be maximum 3 times. So every vertex will only be touched maximum 3 times. Can be just 1 time. Yeah, can be just 1 time. Can be 2 times and maximum 3 times. From parents, from left children if you have left children, from right children if you have right children. That's what that means. The whole complexity, the total number of since every vertex is touched 3 times, the auto operation that you do is 3v. V is the number of vertex, or 3n. 3n. The number of vertex is n. Every vertex is 3 times, so 3n. 3n is just 4n. This is not in your slide, but let me show it here. How many times 15 is executed, is touched? When you start from root, you hit 15, right? And you go left. At the end, when everything on the subtree of 15, the left subtree of 15 is done, from 6 you go back to 15. This is the second time you touch 15. Right. Then you recursively go to the right, 23, 71, 50, and so on. When you are done, you go back to 15 for the third time. So 15 is touched 3 times, and then you stop. How about another vertex? For example, 4. 4 will be touched from 6, go to 4. But your left subtree doesn't exist. And from 5 go back to 4. So you touch 2 times, maximum 2 times. But you can approximate it to 3 times. Okay. How about 5? 5 only touch from 4 go down to 5, and both of the left and right is null. So only 1 time. So it can be 1 time, 2 times, and maximum 3 times. Assuming everything is touched 3 times, every node is touched 3 times. You have n nodes, then the in-order complexity is 3n or on. So you can drop 3. That's how we do it. It's a simple way of explaining things. Now the next, number 5. Question number 5, successor. This is the name of the problem of finding what is the node slightly larger than certain value. What is the value slightly larger than certain target value? The scientific term of it is called successor. What is the next value after this? The next larger value after this. So suppose I want to find successor of 23. The successor of 23, the answer is 50. Not 71, the answer is 50. Because in a sorted order, after 23 is 50. Right? So how do we find 23 in this pair? Right? Successor of 23 in this pair. So suppose you know that 23 is in this position, right? Now, successor means larger. According to BSC property, those that are larger than 23 must be on the right of 23. Right? So must be here. The answer must be here. Must be in this subtree, in this highlighted subtree. But then, in this highlighted subtree are collection of numbers greater than 23. Right? You want the minimum out of this. Okay, I repeat again. 23 on the right of it must be larger than 23. On the right of 23 will be some numbers greater than 23. One of these is your successor. So who is it? The one with the lowest value. So how to find it? Find the minimum in the right side. Get the minimum in this side. The answer is 6. This is the successor. Next, successor of 7. But sometimes you don't have right subtree. So 7 here, 7 is here, right? 7 is here. So I don't have right subtree. So if I don't have right subtree, do you realize that there are several potential cases? I can be here, right? I can be on the rightmost position of a certain left subtree of a node. In this case, 15 is the answer, my successor, and 7 is the rightmost of this subtree. So how to find 15 as my successor? The BSC property say that xt, everything on the left must be lower, everything on the right must be larger. I am the maximum of the left. Means that my successor must be the key, that must be this x. So how to find it? Now here is the first usage of parent also. I have no right house, so I have to go up. I have to find my the first appropriate parent in my successor. I have to go up. I need to keep going up until I make a right turn. If you see it this way, after I make a right turn, means that I have just found the node that I'm looking for. How to find out that I'm making a right turn? If you can do that, okay, you can do that by checking whether if I make a right turn, means that these nodes and me, this node must be 6 must be the left children of 15, so that it's a right turn for you to button. Look at it. Look at 7. 7 and 6. 7 is the right subtree of 6. I can only make a right turn when this property finishes. This is the idea. One more example before I show you the pseudo code. 71. 71 also don't have right children. So I have to repeat the algorithm. I keep searching for the parent until I make a right turn. So then I already fixed the rules before I made it to it. Means that 71 is the largest element in the entire field. Okay, I don't have any more to say. This is another OH. This is another OH function. Let's look at the code first. If you have a right subtree, then you run find me. Find me is OH, right? Find me is OH. If you don't, then you start comparing yourself with your parent. Compare yourself with your parent. As soon as yourself is your parent left, no longer parent right, that's the end. Means that you have just make one turn, one difference. eventually you cannot find it, it's okay. You are this value itself is already a max. And that is how it is. This is OA. OA case. But in the worst case, you can start from the root and from the deepest tree, going up until the root, and decide that I have no potential. Right? So it can be OA. Predecessor is another term. What is the what is the value smaller than the target value? So for example, the predecessor of 23 will be 16. The predecessor of 7 will be 6. Predecessor of 71 will be 50. Just because the whole thing away. Find the maximum of the left subtree, or keep going up until you make a left turn. So it's all mirror of the predecessor. Now the last one is dilution. Okay. I will start with the simplest possible case. There are 3 cases for dilution. If you just if 5 is the read, you just delete it. You just remove it. Very good. But what's the complexity? 8, because you are delete 5. You need to first search for 5. Searching itself will be 8. Now I want to delete 71. First I have to search for 71. I found it here, there. But 71 has one left count, 50. If I just delete 71, it will be opposite. I suppose I have a daughter. Her name is Kate. Suppose I pass away. And my wife also passed away. She will be an orphan. She will have no more parents to take care of her. So, if you have a children, you have one children, and you know you are terminally ill, but your parent is still means that you are going to die. You have one children, but you know that you still have your parents. Then the most logical thing is to let your children be taken care of his or her grandparents. So you ask 23 is the parent of 71. Hey 23, can you take over of 50? And I will disappear. So that's the analogy, the real life analogy that you can probably relate. Dilution with one method. You have one children, you are going to die, but you still have your parents. So you ask your parents to take care of your children. Again, it is OH and some O1 pointers on the page. Detailed case. So now, what if I have 2 children? I have 2 children, not just one. If I delete 15 like that, do you realize that I have now 2 groups of children separated? So the tree becomes disconnected. You have 6, 4, 7 as one subtree, and you have 23, 50 as another subtree. They are now separated. It's also a case of in real life happening in wealthy families. A very wealthy parent has many children, and they pass away without writing proper will or something like that, and the children become fighting each other to get the inheritance. So you don't want that to happen, right? You don't want that to happen, right? So if you have many children, and you have 2 children, and you know you are going to pass away, you have to first find the successor. Find the successor to replace you. Right? So the same thing happening here. 15 is going to die. 15 is going to pass away. If you just delete 15 like that, you are going to create 2 subtrays. And that's not good. So you want to keep, you want to find someone to replace 15. And that someone, oddly enough, there are 2 possible cases. One of the candidates to replace 15 without changing the property of DMC is the successor of 15. The successor of 15 happens to be 23. So you ask 23 to take over 15. Okay? Why is this true? Why the successor of 15 can replace 15? Because by asking successor to replace
yourself, you are going to have duplicate entries, right? 15 gone. Then and you ask the processor to replace 15, then you have duplicate entries. Now look at the structure of the tree. It still doesn't violate the DFT property. You pick any random children or any random nodes to replace you will probably create a wrong DFT. But taking the processor will not violate it. Actually, there's one more candidate, predecessor. You can also use your predecessor to replace it. But for the sake of story, because I want to link it with real life, it's better to use your successor rather than your predecessor. Right? So you use your successor to replace it. Here I ask 23 to duplicate 23, take over 15. So 15 gone, 15 gone. But now I have double 23. I have double 23. It's not a problem. I just delete the duplicate. And ask my DFT now delete 23. Deleting 23 is not easy, right? Because we only have one children. So 50 take over, so 23, 50 like this. Right? Now, you might ask the next question here. If I have two children, if I ask my processor to help to replace me, and I delete the duplicate of my processor, will that cause a cascading effect? Will that going to be on and on and on again so that your deletion becomes very complicated? The answer is no. Why processor of X can be used to delete the other children? The answer is because after replacing a node with its successor, this successor of X definitely has at most one children. And deletion with one children is very easy. It's at most one children. If it's a leaf, just delete it. If it's not a leaf, it has only one children, then ask the parent to take over the children. The first two indicators of deletion. Why is this true? Some proof. So let me go. I need to look over to put this proof. X has two children. X is the fact that we know. Therefore, X has a right child. Definitely, right? You have two children, means that you definitely have right. Successor of X must be the minimum of the right of C. Based on the property of successor. A minimum element of a DFT has no right. So this successor of X definitely has no left subtree on the left level. It can have right subtree, but it cannot have left. So that's why the successor of X has at most one. Can be 0 or can be 0. Got it? If you still don't get it, you can go through this proof line by line again and I'll show you. So deletion, if you write it, it will be slightly longer, but the idea is this. Okay? If this is what you are looking for, go to the next slide. Other than that, you recursively go right or left as per the other slide. But if this is what you are looking for, you decide. There are three cases. If T left now and T right now means I'm a leaf. If I'm a leaf, it's deleted. If I only have one right child or only one left child, bypass me. Other than that, find the successor and delete the successor. So this is a summary. And again, it's also run in O8. Because all operations involve scanning the tree from root to leaf, root to leaf. So this is the comparison of what we have did in the first hour and in the second hour. Now look at that on the rightmost corner. In order to have also is ON, so the rest is OH. And I haven't decided, we haven't seen what is H. H can be as worse as N. So if H is really N, then DFT is poor. Right? It's not all depends on H. Next lecture, I will spend 1.5 hours talking about how to make H equal to long N. That's next week. Okay, so next week I will do the demo of DFT in terms of coding, and also link it to FPLC, the balanced DFT. Now I will explain the game system a bit before I dismiss you. I will take about 1 or 2 minutes. So, if you have laptop or when you have Sign Labor, you go to web link, click cs2010 dns.com.usd. Okay, 2010 dns.com.usd. Use Facebook to log in. This is my view, so your view will be different. Log in with Facebook. If you don't like Facebook, just create a dummy account just for the sake of this module. After this module is over, you can deactivate the account. Right, you will be taken to a registration page. Search for your matrix number. Then there is a verification system. An email will be sent to your NUS email address. You have to click verify. So someone else can log in for you, but someone else can register for you, but you are the only one to verify it. Open your email address and click the link. Now this is the interface from my side. From your side, it will be slightly different. I will highlight achievement errors. The mission first. There will be 9 problem sets. 9 problem sets like this. Okay, from 1 to 9. 8 of them are normal. 1 is bonus, so you don't see optional. Right? The timing of the release date and deadline are already with this slide on this column. Okay? Look at the release time and deadline here. So one by one they will be open and you can download the file. How to do? You download the file. When you write the Java code, you upload to the system. The tutor will grade and give you marks on this system. Then you will get levels, experience points like the game, and you can also get some achievements. So some achievements is like this. There are 5 achievements. You are on track if you do the first 3 missions on time. You are work hard during research week if you do the PS bonus, the very hard PS bonus. So you spend your research week handling this problem and you get this achievement. Unity Singapore, you do all the bonus points. By definition, the R people are careful. The definition is here. You did all the bonus points for PS 1, 2, 3, and 7, and 8 here, plus the bonus PS. You do all this, you are unique. Another achievement is to reach level 15 before even doing PS8. And then the last one is dynamic programming master. You do all 3 PM related to dynamic programming. Okay? So do that. Please sign up before next week. We already put your metric number here. But we don't have your Facebook account, so you are the only one able to complete the registration. Right? Do this, and then next week you will be able to start looking at the first PF. First PF is the baby name. Given a lot of baby names, tell me how many names start from a certain letter. Medium. How many names start with a certain prefix? For the R student, how many names have a certain substring? And what do you need to answer all this? Everything is structure. Okay? So more details next week. And this is the problem that you are going to discuss. You are going to spend about 8 days doing this. About the names. When you have babies, people will start giving you names, right? You Google a lot of suggestions of baby names, you have thousands of them. Which one that you have to pick for your future baby? That's the point. Okay? Stop here. We'll see you again. I'll see you again.
few days ago. Do y'all change anything after that?
You